So we'll continue today finishing up a bit this optics refresher, or maybe for most of you not a refresher but introduction to optics, because you need to know the basic optics in order to explain how optical sensor works. So we explained, to recap, we explained last week the different type of reflection from materials, specular or mirror-like reflection, diffuse reflection, retroreflection. We started talking a little bit about lenses, cameras, lenses. So let's just wrap up the part about lenses, and then we start talking about sensors, using them, and then we'll have another very quick optics refresher about diffraction, and then we'll talk about sensors using diffraction or interference. So basically what we are doing, the first part is what's called geometric optics, and then we'll talk about sensors based on them, and then we'll do just a quick refresher on physical optics, and then some sensors based on them. So the last thing we talked about, we said if we have a lens and we place an object here, okay, and we want to know what the image will look like, the fastest way to know it is you draw two lines, one line like this and one line through the center of the lens. So you're drawing two rays of light, and the reason why the fastest is to draw these two rays, because it's very easy to know what happens to those two rays, because a line going through the center of the lens keeps going unchanged, because the center of the lens is equivalent to a pivot point. The light is going through it unchanged. I mean, strictly speaking, the line actually bends a bit and shifts a bit, because there is still within the lens there is a refraction. But if the lens is very thin, so this theory is kind of a simplified theory for thin lenses, you can say the light through here goes straight through. Now the line or the ray which is parallel, we know what will happen, because in a lens every parallel ray is sent to the focus. So if this distance is f, a parallel ray will be sent to the focal point. It will continue and meet this ray here. So this point, which sends out light rays in all directions, these light rays will all meet at this point. And the reason I know that, if two of the rays will meet here, the rest of the rays will meet here, because that's what a lens does. It images one point to another point. So I only have to take two rays, find out where they meet, the rest of the rays will meet there. If you don't believe me, you can take a point which goes through this focal point. If you take this ray, since it went through a focal point, it will come out parallel and meet here again. Okay? So basically, when you want to analyze what a lens does, it's enough to draw two rays coming out of a point, a parallel ray and a ray through the center, and that's it. So what we'll get here is an image which will be inverted, just simply because the way the rays walk, of that object. And I mean, you can look all this up on the internet, right? That's basic optics. You look up simple lens equations, you see all that on the internet. And we already said that if this distance is called u, that's the common letters used, this distance is called v, you can very easily work out from simple geometry that 1 over u plus 1 over v will be equal 1 over f. And the last thing I mentioned, that the ratio of this distance to the diameter of the lens, or more accurately to the aperture, like there is something here which defines the opening, that's called the aperture. Because in many lenses this is adjustable. The size of the lens stays fixed, but like in a camera there is an iris, or like in human eye there's an iris which adjusts the aperture. So I mentioned that a good parameter which affects things in a lens is what's called the f number, same as in your camera, and that's the distance, or that's the distance to the image divided by the aperture. So in this case it will be V. In this case it will be V divided by aperture. And in a lot of lenses, like camera lenses, where the nominal is that the object is at infinity, so the nominal is that these rays come in parallel, then it's much simpler, because in a camera lens, when these rays are parallel, U equals V equals F. Because if U is infinity, V equals F, and you know that from before, that all parallels come here. So simply that ratio, distance to aperture, simply becomes F over D, okay? And that's what's called the F number. Okay? So that's as far as we went last week, but let's talk a little bit what is the significance of it. So I already asked you a question, what happens if I close down the aperture? Let's say I close down the aperture to make the opening smaller, so somebody already mentioned I'll get a lot less light. That's correct, I'll get less light by the square of the aperture, because the light is proportional to the area it can go through. So if I cut this down to half, I'll get a quarter of the light. That's good. But why do it at all? If that was true, why would you at all want to cut down the aperture and just lose light? But there must be some benefit of reducing the aperture, and I think all of you know that. So what is the benefit of reducing the aperture, or what photographers call stopping down? Yeah? You actually don't, surprisingly, because if you look at this, if you had other parallel rays, okay, let's draw it here separately. If you have a whole bunch of parallel rays and they all come here, now if you stop it down, you are erasing the outer rays, but the other rays, they all still meet at the same point. So strangely enough, it doesn't change the focal point. But and I mentioned it, the very last thing last week, it gives you some, if you stop it down like this and you stop the outer rays, it gives you two benefits. I'm sure all of you used the camera even before cell phone days. Yes? Depth of field. Depth of field. Okay, so what happens is, if you have if this was, for example, the CCD of a camera, this was the object, there is only a certain range where it's in focus, especially on close-up. Okay? So here, it's hard to demonstrate it here because this actually has a high depth of field, but if I look through a microscope, if you take your cell phone camera and try to image something close by, you see it's very, very sensitive to focus. Okay? So the depth of field means how far can you go left and right from focus and still get a good image. So the easiest way to analyze it, you take something at infinity. So if you take a lens and you take something in infinity, which means these rays are parallel. The same reason why the rays from the sun look parallel, because the sun is so far away that it doesn't matter that theoretically they're not exactly parallel, they're spreading. But the sun is so far away, it doesn't matter. Okay, so if you do this, and the rays continue, of course, okay, and you define in focus by some arbitrary criteria. So there's a point at infinity which becomes a point here, but if you go out of focus, the spot will become bigger and bigger. So you just set an arbitrary criteria. What do you mean in focus? Let's say that the spot can only grow by 50%, or if you have certain lines that you can resolve them. So let's not get right now into the criteria, what does it mean in focus, but I think everyone knows intuitively when they feel this picture is well enough in focus or not. Okay, so let's say if I had two circles, if I had at infinity two circles, two dots, and I want to resolve them. In focus, I will see two dots, so clearly I'll call this in focus. But as the dots get bigger, they start merging together. And then if they merge together, okay, the distance is not going to change, but they're going to overlap more. So obviously if these two circles are merged together, I will not call it in focus. Okay, so now it's clear that it's a simple geometric calculation. I know this angle, so I can very easily calculate at what point I wouldn't call it in focus anymore. And it's equally clear that if these lines made a shallower angle, say instead of this angle, if these lines made a shallow angle, it will go out of focus slower. Because if these lines were very, very far away from focus, you would have to move a huge amount before these two spots will merge together. So because of that, it's equally clear that if I stop down the lens, it is the same as making these lines come at a much shallower angle, and therefore the depth of focus, if I set an arbitrary criteria that when the spot expanded to this, I called it DOF, depth of focus, or depth of field. Field is usually referred to this side, and focus they refer to this side, but it's exactly the same thing. Okay, so if this is the depth of field or depth of focus for the full aperture, if I lowered the angle by blocking the rays, this will be the new depth of field. So this is depth of field 1 for ray 1, and this is depth of field 2 for ray 2, and all what I did to increase the depth of field, I stopped down the lens. Is that clear to everybody? Good. Okay. Now, it turns out that there are many other reasons to stop down the lens, which I wouldn't get into, because in geometric optics there is a whole field called aberrations. The lens don't make a perfect image, they put some color aberrations, spherical aberrations, and if you stop down the lens, the aberrations disappear very quickly. So now I will ask an opposite question. So when you stop down the lens, the light goes down, but that's usually not a problem with CCDs. CCD cameras are very sensitive. But so far I only said good things about stopping down. The depth of field or depth of focus becomes much bigger, aberrations become much smaller. Technically the lens is much cheaper if you only have to make a small lens. So now I'll ask an opposite question. Why aren't all the cameras made with a very tiny aperture, in other words a very large f number? Okay, because so far I said so many good things about stopping down. Yes, please.
Do you have to have a longer shutter speed? Shutter time? Like this much light?
No. First of all, longer is easier, right? In a way, if I want to make up for the lost light in a CCD, the way it's done in a CCD, I leave the shutter open longer to make up for the lost light, but then there is blur. If things move, there is blur. So yes, if you're trying to photograph moving objects, you want a lot of light, so the shutter speed can be very close, very fast. So that is correct, but let's talk about other things like microscopy, all kinds of sensors. But especially microscopy, you're trying to take an object of a stationary thing, so it seems that you will have less aberrations, more depth of focus, which is always a problem in microscopy. So why not, at least in applications which have enough light, why not always stop it down to near zero? If you stop it down to near zero, you'll have infinite depth of focus. As you know, the original cameras didn't have a lens, they had a pinhole, right? Because if you have just a box with a pinhole, the rays of light will form an image without a lens, and you can easily convince yourself of that. Okay, so these had infinite depth of focus. Okay, so yes, it's end.
You always want everything to be in focus?
Can you speak up?
You always want everything to be in focus, and you might not want it.
Oh, that's for artistic effects. Yeah, the answer is maybe you don't want everything to be focused. And it's very true when artists take pictures, they want things.
Not totally done.
Yes, but again, that's for artistic things. But in sensors, you want everything to be ideal. Yes.
You're still losing information, though, right? The aperture becomes filtered.
And why are you losing information? If the picture is in focus for longer, great. So where are you losing information? The information is in the sharpness of the picture. Yes?
Do you have problems with the light bending around the edges of the iris if it's too close together?
You are almost there. Very good. So, there is something else in optics besides all geometric optics, and that's called diffraction. Okay? And it turns out that when you take real-life optics, not geometric optics, if you take real optics, light is actually a wave. Light are not rays like this. Lights are actually waves, and waves behave not like lines which bend nicely, because waves have other effects, and primarily they have diffraction and interference, which is hard to explain just with lines. For example, if I have two lines come together to one point, I'll only get more light, because I have one ray and another ray coming to a point. This point should get brighter, like two flashlights. But if I do it in real life, if these are two lasers, I can get total darkness at this point, because one wave will come at the opposite phase as the other wave. There will be destructive interference. So now we're getting to the essence of it. Because of diffraction effects, because light is not idealized straight lines, it turns out, and again, I don't have the time in this course to really get into optics. I'm just teaching you the absolute minimum you need to understand the next session. But you're on your own if you want to learn about optics, which is a good idea for you. So, what happens when you take a lens and you take real light and focus? It doesn't look like this. The thing doesn't really look like this. But if you really look what happens is something like this. Because the way the waves add up, they add up with an almost parallel area here. And this is the real representation of what happens. In other words, if you draw this as a wavefront, and you draw this now as a wavefront which is bent by the lens, this is the lens, what happens here, you get some equation for this behavior, and if you go and reduce the angle, reduce the aperture, if you stop down the lens, what will happen, indeed, you'll get a longer area where it's in focus, but it will also come to a less narrow neck. So let me draw it. Let's say this is the neck where it's in focus for a big aperture. So when you have a small aperture, it will look like this. It will stay in focus much longer, but the width here of the beam will be bigger. And this width of the beam limits how much it can resolve. Or let's say if I want to focus laser light to the teeniest spot possible. So if I use a big angle, I will get indeed less depth of focus, but the rays will converge to a smaller spot. Now if I use a smaller aperture, indeed I'll get a much bigger depth of focus, but the rays will convert to a bigger spot, because in geometric optics the rays are always drawn as crossing and making a zero-size spot. But this would imply infinite resolution at focus. But a lens does not have infinite resolution. Even at focus, it's limited by diffraction theory, which it's highly recommended you understand it, because it shows up in everything you ever do, not just in optics. This whole diffraction limit. So the rays come together and they are limited to some spot, and that spot is called the diffraction limit. So in other words, no matter what you do with the lens, you cannot make the spot smaller than the diffraction limit. The diffraction limit is the theoretical limit of what this lens can resolve. And I'll give you two very simple formulas, which are simple enough even to memorize, which let you estimate very quickly what's happening with lenses. So if this lens had a certain f number, which we already explained before, okay, the smallest spot you can get, let's call it phi. So the smallest spot you can get is roughly, again it's an approximate formula, is roughly 1.22 times the f number times lambda. Because in diffraction, if you use a shorter wavelength, you can resolve more. Okay? Simply because everything scales. The picture scales, everything gets smaller, the waves get smaller, so the spot gets smaller. And this is the reason when you want to make chips, you are using UV or extreme UV instead of blue light, because when you work at the diffraction limit, you have to make the wavelength shorter and shorter to resolve teenier and teenier objects. And if you look at the history of chip making, they started off with 365 nanometer in the old machines, steppers, and then they went from that to 248 nanometer, which is already invisible UV, and then they went from that to 193 nanometer, which is deep UV, and now they're trying to go to 13 nanometer, which is a huge hassle to do that, because there is no materials which transmit that wavelength. Everything has to be done with reflections. But the reason you have to move to shorter and shorter wavelengths is to decrease this diffraction limit. So roughly the diameter you can get to is this. To give you an idea, if I have this camera and I measure the angle, this size of the lens here is about 3 centimeters, that's about 30 centimeters, so that's an F10 optical system, roughly. So if I want to know what is the smallest line here this camera can resolve, it will be for this camera about 122 times 10, and the lambda will be like the middle wavelengths of the light. This is white light, so the middle wavelengths of white light is 0.5 micron, because that's green. So altogether, if I multiply, I'll get about 6 micron. Right? Because 5 micron times 122, roughly 6 micron. So this camera, the way it's set up, 6 micron is very small actually here, if you think of it. Probably the limit will be the CCD, not the lens. Because 6 micron means if I have here 6 millimeters, it's already 1,000 lines. So here it will be like 10,000 lines, which is much more than CCD cells. So the limit here will not be the lens, will be the CCD. And this allows you to very quickly estimate in a system, is it limited by the sensor, is it limited by the lens, by what? So this is a very good formula to very quickly estimate what the optical system can resolve. And there is an equally good formula to estimate the depth of field. Because now we are no longer talking about the geometric limit, which you also have to estimate, but we are talking about the fundamental limit that no matter what you do, the diffraction limit of the depth of field, okay, is going to be, and again it's very rough, this is even a rougher formula, it's going to be 3 times F number, 3 times F number squared times lambda. So these are the two key formulas you use to analyze any optical system when it works at the limit. At the limit means at diffraction. But on top of it, there are many other constraints like aberrations of the optical system and all kinds of geometric considerations. So there is 2 separate sets of limits. One set of limit is set by the geometric things like aberrations and configurations. The other set of limit is set by wave theory. Right? That's straight from wave theory, and that's called the diffraction limit. And you have to take both into account, because the worst of the two will dominate. You may have heard the saying, this is a diffraction limited optical system. Diffraction limited means that all the geometry is perfect. The only thing which limits it is this. Most optical systems are not diffraction limited, they are aberration limited. Like if I would analyze this camera, which diffraction says it can resolve 6 micron, I'm sure it couldn't, because it's limited by aberrations, and in this case by the CCD. Because purely diffraction limited optical systems are expensive, because every geometric aberration has to be cancelled out. Okay, so this was a very, very quick introduction, but the main concepts to take away is that if you take any optical system, and we are talking about optical sensors, that's what we care about, you stop it down, which means you make the hole smaller, you'll get a lot less light by the square if you're stopping it down, but you will get better depth of field, and everything will become better and better until suddenly you wouldn't be able to resolve anymore, because you're going to hit this limit. So until you hit this limit, things get better and better as you stop a system down. But then, at some point, this, because of diffraction, it can't resolve anymore. Okay, and then things get worse again. And because of that, all real-life optical systems are neither fully open nor fully stopped down. So if you think of your camera in the old days where you can change the f number, okay, the photographers always used to take pictures at f8, f11, although the camera, you can dial up anything from f1 to f50. Okay, f50 was stopped down a lot, okay, so you had problems of light and so on, and f1 you had problems with focus, okay, and other things. So in a real-life optical system, the whole thing is optimized to pick the f number, which is a compromise between all the problems. And that's why real-life optical systems always use some kind of a mid-range f number, say f10. Okay, very few optical systems use f1. For example, a microscope, a microscope at the highest magnification uses f1. Okay, and very few optical systems use f100. Okay. Because again, for reasons of diffraction limit and so on, so most systems use something in between, f10. Okay. Now, why does a microscope use f1, which is very problematic with depth of focus and so on?
Resolution?
Exactly. What a microscope has to do is resolve. That's the main thing. You're not so worried about aberrations. You're mainly worried about resolution. So if you don't use f1, this formula will limit the resolution of the microscope, because a microscope has to resolve 1 micron, typically. Like at the highest magnification, you're looking at germs, you're looking at little cracks, all 1 micron items. So if you look at this formula, this number, f number, has to be about 1. So the resolution will be 1 micron, because that's about 0.5. So that's times this 0.6. So this has to be around 1. Otherwise, you don't get a diameter of resolution spot of 1 micron. Okay? Okay, so anybody who still needs some grounding in optics, please teach yourself that, because this comes up more and more because cameras became so cheap, so popular because of smartphones, that a lot of stuff now is done with cameras. So whenever you do things with cameras, you have to understand this optics I just went over. So now, so to show you that all this stuff is actually useful, we are going to cover 3 types of optical sensors, and they basically represent 3 families. And the first family of optical detectors is simply detectors based on yes?
Microscope.
Okay, thank you. Okay, so we are going to cover 3 types of optical detectors or optical sensors, and the first type is simply what's called split detectors, and you'll understand in a minute what it is. Split detector position sensor. And this is basically the most standard position sensor. That's equivalent of the LVDT in optics. The second type we're going to cover is camera-based detectors. Camera-based sensors. And the third type we're going to cover is interference-based sensors, like mainly interferometers. Okay? And we were not going to cover it in great depth, of course, because this whole course is very short, but we'll spend, say, an hour on each family, and this will be enough to get a general view of optical sensing. So, why did this decide to shut off? Wait a second, I need the camera. Okay. And it's decided to shut down, so I have to do it. Okay. I have to wait till this comes up. But anyway, so the most basic type of optical position sensor is you take two photodetectors. Photodetectors is just a piece of PN silicon junction, for example, like photocell. You know it as a photocell. Okay? And you take the difference between them when a spot of light hits them. So this is a spot of light, say a laser pointer. Okay, projector on, yes. Okay, so these are two solar cells with a spot of light hitting them. Okay, imagine one side of the solar cell is grounded. So one side of each solar cell is grounded, and the other side of the solar cell is coming out with a differential signal. We'll call this A, we'll call this B, just like we did on the LVDT. The polarity is such that they are opposing each other, exactly like LVDT. So this will be plus and plus, this will be minus and minus. So if the light spot is exactly centered, what will be A minus B? 0. Okay, so if the light spot is centered, each signal is equal. Now, as the light spot moves to one side or the other, one gets bigger, one gets smaller, just like in LVDT. This is DC, you don't even have AC. You run this into an op-amp, minus plus, you get the position of the spot. Now, we already learned last week that if I get the position of the spot, I can also get the angle of the spot if I want, and so on. Because if, depending where I put the lens, and just as a reminder, so if I have a split detector here, and this is A, this is B, and if I want to measure just angles, okay, I don't want to measure lateral position, I want to measure just angles, okay, what I do is I put a lens far away, I put something in focus, no, not in focus, sorry. What I want to do is something where I want to do something, yeah, I put a lens here where this distance is f, okay, so if I put a light source here, like a laser pointer, okay, the light will come to this point, to f. Now it will not depend on lateral shift, because at focus all parallel rays come to one point, but it will depend on rotation, because if I take this laser pointer and rotate it, the spot will end up here, but if I shift it, nothing will happen. So this way, with a simple lens, I can make an angle detector which is position insensitive, only measures angle. I can easily do the reverse. With the same lens, I can make a very simple detector which is only position sensitive and not angle sensitive. Okay? And the way I do it, okay, I basically reverse the situation. If I have a split detector, okay, and okay, and so this is an angle detector. Okay, and this has to be F. Now I want to do the reverse. I want to do a detector which is not sensitive to angle. So if I put a lens here and I put here the source at F on this side, so if I have a source at F, so any ray from the source will become parallel. If I tilt this, it would make no difference, because any point emerging from here will become parallel regardless of the angle, because that's the definition of a focal spot, that all the rays become parallel. But if I shift it, the whole beam will shift. Okay, so I'll redraw this. I'll redraw this here to make it clear. So now I want to make a position detector, not an angle detector. So I take the same split detector. This is A, this is B. I put a lens in front of it, and exactly at the focal point F, I put my source. Let's say my source is a laser pointer, or could be an LED, could be any light source. So in this position, if I send the light, if the light goes in all directions, like this, say it was an LED, if I tilt that, it doesn't matter. If I tilt that, it just means that actually it matters to some degree here, because of course the centroid of the beam will change, but the rays will still come out parallel. Okay? On the other hand, if I move that to here, if I move the LED to here, the central ray is unchanged, okay? And all other rays will follow the central ray. So now I'll end up with a beam at a different position. This is more obvious if I move this farther away. The way I drew it, maybe I drew it too close. If you go farther away from the lens, this is a detector. So if the LED is here, regardless of position of the LED, I'll get a big light spot here. Now it is true that if the LED is non-uniform, if I turn it, I'll get the light spot a bit brighter here, a bit brighter here. There'll be small error in position. But if I move the LED to here, this whole beam will actually go now this way. So, because the central ray going to the center of the lens is not changed. So if I move the LED, this whole beam will steer. And I showed it to you last week with the laser pointer and the lens. So now it will be very, very sensitive to position and much less sensitive to angle. I wouldn't say completely insensitive to angle, but much less sensitive to angle. Okay. So you can see that just by placing the lens and the detector correctly, I can make a detector which is either sensitive to angle or sensitive to position or any combination. Yes, please.
So the angle sensor, the light exiting the light source has to be parallel light? Is that from the right? Okay, no.
Here, now you are referring to which one? In the angle sensor, it doesn't. No, I can do it. It doesn't have to be parallel light, but you have to design the sensor correctly. You can do the same sensor with an LED, but you have to design it correctly. That in this case, you have to design correctly that the lens is large enough that it will capture the whole beam. Okay, so it doesn't have to be a collimated source. For example, if I want to make an angle sensor with an LED, which is not collimated source, I can do it. I can do it as well, because if I take a lens, okay, okay, let me draw it here. Okay. For example, if I take an LED and keep it at a large enough distance that it acts nearly collimated, or I'm sure I can come up with other configurations that it doesn't really have to be collimated. It's enough that the LED, I can take an LED and collimate it a little bit. Typically LEDs that you buy already have some collimation built in, because in many LEDs you buy, that's the LED and the plastic is molded in the form of a lens, so it gives you some collimation. It doesn't shine in all, and this will be enough to make an angle sensor, because if I did it this way, it will come to a focus, say, okay, it will come to a focus here, okay, and if I did it, okay, so what is important, that this is not imaging this point, because if this point was imaging this point, in other words, if this is U and this is V, and if 1 over U equals 1 over V with 1 over F, it wouldn't work, because the image of the LED will always appear at the same spot. Okay, but if it's not imaging this point, it will sense angle even if it's not collimated, because if I turn this beam to go to a different part, it will end up at a different part. It will not work only if it's imaging this point. It will work at all other points. Because imaging is defined that this point will always appear here, so you'll just see a smaller picture of the LED always at the same point. Okay? So you can play around with the optics in such a way that you get what you want even if the source is not collimated. Of course, it's easier to explain it and easier to build it if you have a laser pointer, which is an ideal source. But most optical sensors actually are based on LEDs, not on laser, because they're cheaper. Okay, so now let's get back, just a second, I have to get back to the document camera, and let's give you a quick demo of this. So what I have here is, I just took two pieces from a broken solar cell. Okay, forget this. So this is just for the demo. Okay. The reason why, by the way, this always stays in focus is because it has an autofocus built in. So it's not because the depth of focus is so great here, but you'll notice it has an autofocus circuit. When I put it in, to show you it has an autofocus, I can hold it higher and then lower it, and you'll see it coming in focus. See, it goes out of focus and comes back to focus. So you can't give a demo here of depth of field, which that's what I tried to do before, because it has an autofocus which fights you. Okay? On the old-fashioned overhead projector, you could give a very nice demo of depth of field by simply putting this in front of the overhead projector, and you could see that with this you had more light and less depth of field, with this you had less light and more depth of field, but I don't know how to shut off the autofocus here for this demo. Okay, so what it is, just two pieces of silicon from a broken solar cells connected like this, differentially. They're connected one minus the other, and I'll just connect a meter which measures A minus B, and then we have a differential detector. We have the thing there, what's called a split detector. A split detector is exactly that. So connect one side to the other. Like this. And now it should read nearly 0 or 0, because as we said before, if the light falling on both detectors is the same, then A minus B is 0. Okay. I need my glasses already, I see. Oh, this is bent. Good. Okay, so the meter, I'll bring the meter in the field of view. Let it autofocus. It's trying to find the focus. The problem, the meter doesn't show up very well, so I have to play around with it until you can see the meter well. Okay, yeah, now you can see the meter, you can see the red pointer. If you watch on the meter, you can see the red pointer. Okay. I'm just trying to find the face. Trying to find. Here the contrast. Here the meter shows up the best. Okay, let's. Okay, so this whole thing is not so good. Okay, now I'll take a laser pointer and I'll hit the two detectors. Now this is a very sensitive detector. These types of detectors which measure A minus B are very sensitive. So because of that, the meter is going to jump quite violently. It will only be 0 again if I'm dead on. Okay, if I'm dead on focus here. So this is, can you see the laser pointer? Yeah. Okay, and let me stick it on a magnetic base. So it'll be easier to adjust. Like this, and okay, so watch the meter and watch the spot of the laser pointer. So the meter does violent jumps unless the spot is exactly in the middle. It is very, very difficult to do. because watch the spot. You can see the spot just as a bright spot between the wires. So if you look here between the wires, right here, you'll see the spot, which is quite small. And okay, this is a bright spot between the wires. And if I move it, can everybody see that from there? Good. So if I move it the slightest amount, which is barely visible, the meter jumps from one end to the other. So you can see how sensitive it is, that only in the middle, if I'm very, very careful, I can hold it in the middle, and then it reads 0, but the slightest movement, which is barely perceptible, moves the meter full scale. Okay, so this is a split detector, position detector, which can be made incredibly sensitive, because you can imagine if you have a laser pointer which is very bright, and you are amplifying it here by a lot. And interestingly, what I'm showing you is without any amplifier. See, what I'm showing you in this demo, I just take A and B directly and put a meter between them. So without any amplifier, if I have a bright source which hits the detectors, these detectors will create a couple of milliamps each. The meter is sensitive to 50 microamps or so. So without any amplifier, this has a sensitivity of about 1 or 2 microns. Okay, now imagine if you put in an op-amp which amplifies it by 1,000,000, okay, how sensitive this could be. So this meter actually has a linear range. It's not an on-off, because as you saw there, it has a very narrow linear range, but it has a linear range. I can make the linear range much bigger simply by lowering the gain. Right? Because what happens here, the linear range is quite big. It's actually the whole size of the spot. When the spot is all the way here, it's end of range. When the spot is all the way here, it's end of range. So if I make the spot 10 millimeter, it has a linear range of 10 millimeter. Now what happens here, the meter saturates at a very tiny movement, but the linear range is actually very large. Is that clear to everybody? Because if I draw a graph, what's happening here? So let's call the spot diameter D for a moment, and I draw a graph. This is X position, and this is output, A minus B. Okay? So, and let's call the middle X equals 0. Oh, okay? So when X equals 0, the output is 0. Now, as I start moving this, it will keep changing until I moved it by a whole unit of D over 2. So because it's a 0 position, to simplify it, this was a 0 position, and when the circle reaches here, this photocell has no light, and moving the circle farther doesn't make any difference. Okay, so I will have a linear range from 0 until plus D over 2 and minus D over 2. And over that range, it wouldn't be exactly linear. For example, if this was a rectangle of light, if I replace this with a square of light, then it will be completely linear, because assuming the square is uniformly lit. Because as I move that square of light, more and more area is covered by the same intensity of light. So let's say, just for argument's sake, I have the light in shape of a square. So this will look like this, and when it comes to D over 2, it will saturate. Okay, so it will be a very nice linear range. It will be differential, okay? And it could have, I can scale this up any size I want. And let's say I wanted to make a detector which is 1 meter range. 1 meter range is expensive to make a detector this big. But I really want to make it for 10 cents and very small. So how can I make this for 10 cents, very small, with a 1 meter linear range? Because we learned something in the last few hours that enables you to do that. Yes?
You can make the spot size really small and then lower the gain of this optical sensor, and then
if it's far away enough and the spot size is small, then the small spot size of the sensor can traverse the...
You are getting close. What you do, actually, you use the property of the lens that you can image any scene to any scale you want. Right? So you don't have to have the detector 1 meter. What you can do, you can shine a spot size, you can shine the spot on the wall, a big spot for a flashlight on the wall, image it with a lens onto a little detector, and that big spot on the wall will look very little. Right? So if I take this little detector and I put a lens in front of it like a camera which images it, I can measure with this little detector 10-meter movement. So the scale doesn't matter, it's just a matter of one lens and scaling it. Okay? So it's a very versatile detector. Like in an LVDT, I couldn't do that. In the LVDT, if I wanted to measure a small distance, I had to make a small LVDT. If I wanted to measure a big distance, I had to make a big LVDT. You can argue, you can say in mechanical system, you can make a lever. So if you wanted to measure 1 meter, you can make a lever, reduction lever. But it's very complicated because the lever goes at an arc and the lever has mass, it has backlash, it complicates life. But if you do an optical sensor and you put a lens in front of it, you can image the scene to any size you want. The light has no mass, well, it has a little bit, but you don't notice it. Okay, it has no delay, right? So optical sensor, because the image can be scaled to any size, okay, then it's a huge advantage. You can take one detector and use it for all ranges, for all sizes, and you can convert this to an angle detector, or you can convert this to a displacement detector, just like I explained before. Depending where you place this lens, okay, this can become either an angle detector or anything you want. Yes?
If you want to do scale it using imaging and also have the position detector and angle detector,
yeah.
you need 2 lenses, or can you do it all with 1?
Depending how clever you are, but mostly you can do it with 1, but it's kind of tricky. So I'll show you, for example, so let's show you an example where I can do it. Say if I want, in angle detector it doesn't matter, it's always the same. The angle, big or small, is always the same range, plus minus say 90, but in position, okay, so if I want to make a position detector which is insensitive to angle, so let's see if I can do it with 1 lens. Let's say I have a laser pointer or an LED. Let's make it simpler. I have a laser pointer and I want to move it 1 meter. Okay? I want to move it 1 meter, and I want to do a differential detector, but my detector is only 1 centimeter. Okay? So if I did it the classic way is like I drew it, I need a lens which is 1 meter. Okay, so that's expensive. So the way I would do that, of course, I would shine this spot on a white wall. So this will be the spot on the white wall, and then I'll put a lens here which images this onto a small picture. So I can still do it with 1 lens, but I need a wall to image down to, because if I don't have this white wall, the lens has to be as big as the travel. Okay? So that's an example that depends how clever you are. In general, in optics, there's a lot of room for cleverness because you have all kinds of unexpected tools that you don't have in mechanical things. So I would say with some cleverness, for $1 you can make an optical detector for any size, for any property, for any angle, for any range, right? And I'll show you a few other tricks later that you can make it immune to noise and immune to everything. So the potential here to do clever things is much bigger. Okay, and that's the reason, as I mentioned to you before, today if you look around in industry and everywhere, let's say half the detectors are optical, half the detectors are electromagnetic, capacitive, inductive. But by the time you'll be in mid-career, okay, I would say 90% of the detectors will be optical, because there is more. The trend is such that there is more and more innovation going into optics, like laser diodes, cameras. there is not much left to innovate in coils or capacitors. So basically, and so cost-wise and all the things we discussed about is shifting the balance where detectors go into optical. So anyway, it's clear to everybody what this is, how it works, right? Now it's also clear to everybody that they can immediately take this idea and make it in 2D, because I can make a detector which is split into 4. So this will be A, B, C, D. Okay? And then I have a spot here, I can measure X and Y movements. Okay? And if you think 2 more minutes, you realize that if I have a detector A, B, C, D, if I take A plus B minus C plus D, if I take this measures vertical, this measures Y. Because if I measure Y, I don't care if the spot is here or here or here, I just want to measure the spot in this axis. So I sum A and B. And then it's also clear that if I do the other way, if I take A plus D minus B plus C, then I measure X. So all that I need is 2 op-amps, right? One which does this operation, one which does this operation, and I have simultaneously X and Y measurement. Right? Is that clear to everybody? Because it's a linear system. You have to remind yourself what does a linear system means. Linear system means linear superposition holds. So the definition of a linear system, the mathematical definition, So, let's hear some opinions. Yes?
A should be minimized.
But how critical is it? Because it's hard to make it when you build a detector. So let's say I can't make a 1 micron gap, I can make a 1 millimeter gap. Will the detector suffer a lot or not?
Sensitivity.
Pardon?
It would be less sensitive.
Okay, so let's put it aside for a moment. Let's talk about D. I want to build a detector which is super sensitive. Super sensitive means I want to measure 1 micron movement, highest signal to noise. A as small as possible and make these as similar to A, so the slightest movement will make a big change. Okay? So most people, when they design a detector like this, they do this. They make a very small gap and make D equal to A. Now, so the surprising answer is that A doesn't matter at all, and the best performance is that D is the biggest. Okay? And the reason is, I explain the reason. First of all, it's a differential detector, so even if you make the spot this big, and you make A almost as big as the spot, you're just wasting light, but besides wasting light, you're not losing any sensitivity, right? Because this detector is exactly the same. This detector is exactly the same as a detector which has a very small gap and a spot like this. Because this and this, the detector sees the same thing, right? They only see this. Okay? So the only difference, you're wasting light, which is very cheap these days, from LED. The first surprising conclusion is that matter at all, so you don't have to make the two detectors lithographically spliced to perfection, you can just stick them together. Yes?
The size of D doesn't affect the linearity.
No. Because think of this. If this moves a little bit, like this, or this shape spot moves a little bit, if you have the detector, you don't even know whether the light came from this or from this. It doesn't affect at all the linearity. Again, it's kind of counterintuitive. It takes a few minutes to think through it, and it doesn't matter at all. Obviously, you don't want to waste light, so you bring them together, but it doesn't affect anything. Another way of thinking of it, if this is confusing, think of it this way. Think that you have a rectangular illumination. You have a rectangular spot of light, and you have one detector here and one detector here, and this is a huge A. So this spot moves, so all the detector sees is two small spots which are moving together. The detector doesn't know there's a lot of light wasted in between.
So at some point, wouldn't you have, if the gap is large, only light being on one detector, while still being able to move within the gap?
But this will happen with this too. If you have one spot with a teeny spot here, if the spot moves to here, the other detector is there. The same thing. Anyway, it takes a few minutes to think about it to convince yourself that surprisingly A doesn't matter at all, which is contrary. Yes, please? Yeah, but it's separate. If you think a big D, then A doesn't matter. But the more surprising part of the discussion is why is it better to use a big D like this for making very, very small, accurate measurements? And that is the most surprising part. Because A, you can convince yourself that it doesn't matter to make the spot bigger. But why is this better than a teeny focus spot, which the slightest movement will change the light a lot? Yes, okay.
I guess if you make it like too small, it becomes basically like a binary detector. It's basically either one or the other. So if you increase the size, you're kind of increasing the range.
True. So yeah, so in one way you limit the range. That's very true. But let's say you want a small range. Let's say you make the spot 100 micron. So it's not a binary detector. It still has a 50 micron range. And versus this, which is 1 millimeter, let's say. Okay, so this is 10 times bigger spot. But you only want a 100 micron range. You're right about if the spot is small, you can never have a big range out of the detector. But let's say you don't need a big range. Yes.
You need to move a smaller distance with a larger D.
so that you're more sensitive to your position because you have more light for laser circles. Does that kind of make sense? So like you're more sensitive to your emotion with larger D.
Yes.
You have a higher signal to noise ratio, don't you, when the D is larger?
And why?
There's more light energy that's being read by the sensor, by the detector.
But you can put all the same light into a small spot, so its C ratio is the same. So I think you're thinking too high level. You're thinking about, yes please.
Sorry, would it just increase the voltage output of the thing so it may get more sensitive?
No, but let's say that all the light is shrunk into a smaller spot, so the sensitivity is the same because you have all the light and put the same current. I think, your thinking reminds me of the story that Einstein and his wife went camping, and in the middle of the night, they went to sleep. You probably heard this story, right? And then, anyway, they went camping, went to sleep, and they wake up in the middle of the night, and they see a starry sky, and Einstein's wife says, "My husband, what does this starry sky tell you?" And they were camping. And Einstein says, "Well, I see billions and billions of stars, which means the real number is infinite, blah, blah, blah." And his wife said, "What an idiot. He tells us somebody stole our pen." so you find the thing. Now, the answers in these things are much simpler. Okay? So basically, there is always think of real life, of practical things. The detector is not perfect. The detector has unevenness, has some defects, has some scratches, some dust falls on it. The light isn't perfect, because when you look at a spot of light, the spot of light itself has some aberrations, maybe has some contours of intensity which are not perfect. Okay? So, the way to get accuracy out of imperfect devices is by averaging. And this is a principle which is true for all sensors. The more you average, the more accurate you get, because you know from theory of errors, if you have a lot of random errors and you average, if you average n values, the accuracy improves square root of n. And you should have learned that in some course in statistics. Okay? So in an LVDT, without thinking, you have averaging. If LVDT has many terms, the signal is a sum of signals from hundreds of terms. You get averaging. That's one reason it's good. In a capacitive sensor, you're averaging, because you have a big area moving, two big plates. You're averaging the signal from the whole plate. So in a capacitive sensor, if the plates are imperfect, which they are, and there is a piece of dust sitting here, you average the whole area. Okay? Now, the same thing is true for optical sensors. The way to get accuracy is a lot of averaging. So, if you consider the fact that if you now take a real-life exaggerated view, the real-life exaggerated view looks like this. The gap is actually not perfect because the edge has a roughness and the silicon was cut. So real-life view is like this. The gap is not perfect. There is some dust spots or defects you cannot help. And there is a light spot, which is also not perfect, which you cannot help. Now it's clear that if you take a big spot, you don't see the roughness of the gap, you don't see the dust. Okay, you average. If you take a very small spot, you get a very beautiful sharp spot, but if it moves and it hits a part of dust, you get a huge error. So the practical reason why it's better to make a big spot is two reasons. A, averaging, and secondly, a reason you didn't think of, and this I didn't expect you to think of, because silicons will saturate. But if you put all the light in one spot, the spot will saturate, so actually it will not work at all. Because you have to be very careful not to saturate the silicon, otherwise it stops being linear, and my theory of linear superposition stop working. So to give you an idea how quickly silicon will saturate, okay, is like this. A typical solar cell, or typical silicon sensor, is designed to work in sunlight, which is about 100 milliwatts per square centimeter. So most silicon detectors are designed to work up to 100 milliwatts per square centimeter. But if you take a laser pointer and don't focus it, you already get a lot more than that. And if you focus it to a smaller spot, for sure the detector will saturate and not work at all. Okay? So A normal laser pointer is a 3 millimeter spot, which is 10 square millimeters, okay? And it has, let's say it has 10 milliwatt 10 square millimeters, so it has 1 milliwatt per square millimeter, okay? So it's about right, 100 milliwatt per square centimeter. But the moment you focus it on a small spot, it doesn't work, it saturates. Okay? Now, especially if you want to move, you want to measure a 1 micron movement. Now, if you, and you really want to make it the gap 1 micron and the spot 1 micron, then the power density will be 10 to the 6 higher than that. Because now you take a 10 milliwatt and go to a micron instead of a millimeter, okay? Say 1 milliwatt to a micron, so instead of getting a milliwatt per square millimeter, you're getting a milliwatt per square micron. Okay? And the difference is 10 to the 6. So basically what it means is that any focusing of a laser pointer to less than a millimeter will stop working. So that's again, that's a practical consideration. When you think of a detector, you always think it's linear. But it saturates. The same thing, by the way, can happen in an LVDT, but it's less likely. Because theoretically, in an LVDT, you can run the excitation coil. It's much harder to saturate the magnetic material in air than it is to saturate the silicon detector. So remember the rule of thumb that a laser pointer pointed at the silicon detector, even a cheap red laser pointer, that's already saturation. So that's already not safe to do with an accurate sensor. But even a normal laser pointer, you have to expand the beam maybe to 10 millimeter to be absolutely sure you don't saturate. You can always tell saturation by plotting a graph. You just increase the power, you do P in and I out. Okay? And you see right away, it should look like a straight line, but you see right away that it looks like this. So you know what the maximum light power you can use. Okay? Okay, now the last thing I want to tell you is some rule of thumb, another rule of thumb which is very, very important to design these detectors, because most people don't have an order of magnitude idea. If I take a laser pointer and shine on a piece of silicon for the sensor, the laser pointer is in the range of milliwatts. All laser pointers are like 1 to 10 milliwatts. Okay? So if I shine a milliwatt of light on the detector, what current do I get? Because you know that these things, the detectors, they convert light to current, not light to voltage. So it's incorrect to use them as a voltage mode in a design. Because the voltage will reach 0.7 volts and saturate very quickly. But the current will keep going up until it saturates. So what really you use those is the current mode, not voltage mode. Okay? Is that clear to everybody what I mean by current mode? You use it as a current source, not as a voltage. Okay, so if I shine a 1 milliwatt laser pointer at a piece of silicon detector, do I get a microamp, a milliamp, an amp? How much do I get? What's your guess? I mean, yes? A million. Good, you get less, but you're close. Well, you know, one way to easily estimate it is by energy. If I shine a milliwatt on a detector, I cannot get more than a milliwatt out. It has an efficiency, I probably can only get efficiencies. You know, efficiency of solar cells is like 20%, the best. So I can only get, if I shine a milliwatt, I can only get out 0.2 milliwatt, right? And since the voltage is less than a volt, I can get maybe a bit more than 0.2 milliamps. So just by looking at energy in, energy out, you get an idea what current to expect. But a good rule of thumb is to assume that I out equals 0.4 of P in. This is in amps, and this is in watts. So if you shine a watt of light, you get 0.4 amps. And if you look at the data sheets of sensors, it's always specified as amps per watt. When you talk about sensitivity, you say 0.4, 0.3 amps per watt. they shine a milliwatt, we get 0.4 milliamp. But this also, we got the same result by energy consideration, because we said since the efficiency is maybe 20%, if we shine a watt, we should get 0.2 watt. Since the voltage is less than a volt, it comes out. So to get 0.2 watt, we need about 0.4 amps. So either the way you look at it as energy from common sense, or you look at it by the small sum, this is the basis of designing the sensors. So you get. So that's why this meter here was moving so violently, because this is a huge power laser pointer. So this is actually a 100 milliwatt pointer which saturated the silicon. So I got out of the silicon only 10 milliamp. The meter is 100 microamp meter, so the slightest movement saturated the meter. Okay? Is that all clear? Good. Try to read up on optics on the internet, because a lot to cover. And the more optics you catch up quickly, the more you know the sense.